Morning, everyone. So yeah, thank you for inviting me, for giving me this opportunity to talk. So I'm Sho Sugiura, the CEO, co-founders and CEO at Blocq. So we are a quantum software company. Do you hear clearly? Okay. Yeah. And let me introduce myself a little bit. So I'm the CEO at Blocq, but Blocq is kind of new startup. Like we have founded last year, and before starting, I was a physicist, a quantum computing physicist, and I got research our like Japan Physical Society, Tokyo University, and they're like he's the emperor of Japan, so I got a lot from them. So if you have any question about quantum computing, please ask me. I can answer any question. So let me start my presentation, my talk. So today's talk, I don't go into too much detail about technologies, but I just try to give overview of the quantum technological current status of quantum technology, quantum computing technology. And first of all, why quantum computing is so strong? Maybe you know about this, but superposition is the key. So quantum bit or qubit is a basic unit of quantum computer, and quantum bits can possess many states at the same time. So they can do a calculation parallelly. Like when we have 10 qubits, we can have quantum qubits pose 100,000 different states, and they can calculate thousands. They can process thousands of states at the same time. So that's the power of quantum computing. And at the end of the day, we need to see the result, and interference performs a critical role to get the result. So we do parallel computation, and by using interference, we boil down to one important result. That is the basic philosophy or mechanism of quantum computing. And quantum computing has, roughly speaking, 3 different types. So gate-based quantum computer, and measurement-based quantum computer, and quantum annealing. And gate-based and measurement-based quantum computers are the mathematically equivalent. Of course, the hardware are very different, but mathematically equivalent, and they are universal, which means any quantum computing calculation can be performed by these universal quantum computers. And quantum annealing is a device specialized for optimization, which is not universal. And it was popular, but it's not very popular anymore. And I think the mainstream are these 2 types. And gate-based is the most popular one. IBM and Google and some other quantum startups are working on. But the difference is kind of tiny. So we have circuit, but essentially operations are done by quantum gate operation or measurement. That's the only difference. And measurement-based quantum computation, photonic platform, photonic quantum computing companies are working on measurement-based, and other architecture like superconducting, ion trap, neutral atom, they're working on gate-based quantum computer. So, but building quantum computer is hard. There are many challenges, especially decoherence and gate errors are the biggest bottleneck for us. So first of all, so as I said earlier, qubits can possess superposition. We can process many states at the same time. But this superposition is fragile against noise. It's extremely sensitive to environmental noise, and it will break the calculation. Then we can't do calculation anymore. Currently, gate error is quite good, like 99% to 99.9%. So we only have 1 error in 1,000 times of operations, but it's still not enough. We need error rate like 10 to minus 10, 20, so it should be extremely good. To achieve that, error correction is essential. So error correction is the technology our community has been working on since 2020, so for 5 years. But error correction is hard because we have making 1 error-corrected logical qubit consumes thousands, hundreds to thousands of physical qubits. This distinction is extremely important. So naively, error correction is very simple. Like it's just like a majority vote. Suppose we have we want to encode one to one qubit, then we can just like make 10 physical qubits encoded in which one is encoded. So we just like have 10 ones. Then if you see one is flipped to 0, but you can do a majority vote and correct the error. So this type of majority vote is the essential idea of error correction, but it requires a lot of physical qubit to make up one logical qubit. So this is a distinction. And there are some more hardware limitations, like superconducting qubit connectivity is a problem, like only qubits in superconducting qubits, in superconducting architecture, only nearest neighbor qubits can interconnect each other. So the connectivity can be very complicated, and also there are a lot of infrastructure problems like refrigerator or laser, or how to scale up. These problems are, of course, we need the challenges. But these three are the major challenges, in my opinion. So let me talk about the tech stack. So, by the way, I need to check the time. Okay. So what's the? Yeah. Okay. Sure. So, and let me talk about the technological stack. So, quantum computer, roughly speaking, we have three layers of technological stacks. So, software and middleware and hardware. So let me start with hardware. There are so many different type of quantum computing hardware. That is one reason. Yeah, that one reason it's confusing to understand. But essentially, as long as we can control states precisely according using quantum mechanics, we can make a quantum computer. So in a sense, superconducting, neutral atom, trapped ion, photonic, and other qubits can be worked as can work as a quantum computer. That's why there are so many different types. But these four are, in my opinion, the most popular or most promising candidates. And superconducting qubits is the most popular one, like IBM and Google are working on. The advantage is speed. But there is a problem about the stability, scalability, and connectivity. So they have logical qubit, but interaction between two logical qubits hasn't been established because superconducting qubit is installed on 2D surface, so the interconnection is like very limited. And neutral atom and trapped ion are similar structure. They essentially they trap the atom or ion by laser. So it's called laser tweezer, optical tweezer, and they can move around these atoms. So this atom or ion is used as a qubit, and they manipulate these states by shining laser on it. So this is very different technology for superconducting qubit, but as you can imagine, it's very flexible. It has very flexible structure. So speed is very slow, but stability is good, and scalability is also good for neutral atom. So actually, 2 years ago, neutral atom architecture, so a company called Kuera realized first error correction, and they already have 10,000 qubits in one physical qubits in their quantum hardware. So in that sense, this is a rising star in quantum hardware. And trapped ion is extremely stable. It's more stable than neutral atom, but scaling is a problem because this is packed into one-dimensional chain, so it's very hard to scale up. So, but once they solve this scalability problem, this is very promising architecture too. And these two are using like atom and ion, so which is like most stable material in the world. But superconducting is more like a fabrication. They are making a material to make it work. And photonic is a little bit different. They have very different strategy. They don't have any problem in scalability, but current stage, their error rate is relatively higher than other architecture. And basic error correction has been done in these three architecture, but it hasn't been achieved for photonic. But they have totally different structure. Once they overcome this stability problem, making a million of qubits is easy for a photonic device. They can try to catch up and overtake all these architecture afterwards. That's their strategy. And let me talk about the error correction part. So surface code is by far the most important one. So all the companies are working on surface code. And Google has demonstrated their first error correction demonstration on Willow chip on surface code. But the problem is they consume a lot of physical qubits to make up one logical qubit. Essentially, hundreds to thousands physical qubits is required to make one logical qubit. So that is a big overhead. But recently, most popular error correction code is called QLDCP code. Then they can make one logical qubit from 10 to 100 physical qubit. That is way efficient. So many companies are working on this architecture right now. So seeing the progress of QLDCP code is also important to assess the progress of quantum computing. And the software stack, there are many SDKs, and we can make you can start making quantum algorithm from today, I think. So Qiskit, CRQ, Ticket, QSharp, PennyLane, they're developed by IBM, Google, Microsoft, and so on. So many, all tech companies are working on this type of quantum computing recently. So they have very easy to use SDK, so you can play around and you can use simulator to see the performance. So let me move on to application. So let me talk about noisy intermediate scale quantum computer. It's called NISQ in short. It was actually a kind of nightmare for quantum computing community. So it was a quantum computer, or it is a quantum computer without error correction. And people expected we have good application using a NISQ device like quantum chemistry or combination optimization program or machine learning. But it turns out that noise is so large that we cannot do any meaningful calculation. So essentially this project kind of failed. So quantum computing community shift our focus to error correction. So in a sense, it was a dark era of quantum computer. But we do have a clear roadmap towards error corrected device, which is called fault tolerant quantum computer (FTQC). So this is a roadmap from IBM. You can check out. I can tell you about different companies' roadmap, but IBM has the roadmap towards 2030. So in 2029, they announced that they are making free fault tolerant quantum computer (FTQC), and they scale it in 2030. That is their roadmap. And before that, they are making a component one by one, like they start to develop QLDPC code and they make a one logical qubit and they scale up. That is their roadmap. So of course there's a lot of things to do, but we have some sort of clear step towards FTQC. And Google already made a one logical qubit like last year by Willow, and some other quantum hardware companies has slightly faster roadmap too. And so you might think, 2030 is far away. And, last year or this year, we had a buzz about Google's Willow chip and also Microsoft's Majorana chip. So let me comment about it briefly. Actually, Willow is a groundbreaking innovation in our community. So essentially, but this is not we don't need to worry about it right now, because this is Willow chip only has 100 physical qubits, and what they performed was one logical qubit operation and successful error correction. So they have one logical qubit right now, but they haven't succeeded to connect two logical qubits, and this is very this requires a lot of complicated wiring, so this hasn't been established yet. Some other platform like neutral atom and ion trap have already realized that kind of interconnection between logical qubits, but it's still very small. So in a sense, we have logical qubit, but so even though we have 100 physical qubits, we don't need to worry about it because we only have a few logical qubits for now. But scaling up this logical qubit will lead to the real quantum application. And when it comes to Microsoft Majorana one chip, well, this is scientifically innovative, and but they just made one single physical qubit. But this topological qubit is extremely can have extremely high low error rate, like 10 to minus 10, 20. So logic error correction might not be needed, but they just made one qubit and they haven't performed any operation on that. So in that sense, it's very primitive. So yeah, good to see the progress, and we should observe the progress. But it's I would say it's very primitive.
How is the connectivity between these two?
They just made one physical qubit, and people are arguing about even the existing of qubit itself. So making the operation on qubit hasn't been established yet. So I think, in my opinion, these two are very different. And the last part, this is about the application. So this is we edited a little bit to show the better visibility, but this is from DARPA's results. So DARPA's quantum benchmarking initiative, it's like a government program, and each point represents a different application. And horizontal axis is number of logical qubits required, and vertical axis is number of operations required. So we are currently around here, so there's, I would say, no application for FTQC. And you can see different applications and chemistry and magnetic simulation. They are like quantum analog simulations. They have many applications, but look at these 2 points. These diamonds are decryption. So RSA and ECDSA are not like very difficult program, and especially for ECDSA, it's around 10 to, it's like thousands. So once we have 1,000 logical qubits with enough error rate, like 10 to 15 to 20, then decryption will, so quantum computer will hack the ECDSA. So as you can see, there are many applications, but actually ECDSA is one of the easiest application for quantum computer. So actually this split between RSA and ECC, as I would say ECC, is kind of overlooked in the community, but recently people realize that this is way easier. This is because of the bit length. RSA has 2048 bit, while ECDSA has 256 bit for the same security from the classical attack vector. But quantum computer is doing more like a brute force. Then number of combinations are way smaller in ECDSA, so it can fit into smaller quantum computer. That's why it's easier than RSA. So that's the current situation in my understanding. So that's it. So final takeaway is kind of abstract, but as you can see, quantum computing is real, but there are so many things to do, so you don't need to worry too much about it. But at the same time, probably it's not a good idea to ignore it. So because we have, from outside, you might think it's like a hype cycle or like go up and down, but actually inside the community, technological stacks are gradually developing, and once we reach to the threshold, we have real quantum application. And looking at the timeline, probably next 5 years, quantum computing hardware companies will set up more concrete roadmap towards FTQC. So that's its best help to assess the progress of quantum computing. Okay, that's it. Thank you very much.
Thank you. I think we might, if there's a super pressing question, see that hand, Max. What is it? What's up?
As we think about, for someone that's not deep in the field, close quantum.
Yeah. Here, Max.
Thank you. So you talked about how we're going to break ECDSA. RSA has more bits, so it's going to take more time to break it. As you think about post-quantum cryptography, do you think it's always going to be an arms race where we just get more and more bits with new forms of cryptography? Or do you think there's going to be fundamentally like new breakthroughs in cryptography or completely new approaches that are the long-term solution?
From the viewpoint of quantum
Yeah.
computing, is fundamentally different. So ECDSA and RSA use essentially the same problem of period finding. So we use the same algorithm, but it's vulnerable against quantum computer. But other PQCs use fundamentally different mathematical problem, and there's no known quantum algorithm that efficiently solves the problem. So it's fundamentally different.
Thank you. I'll say if there's other questions, hold them for now. We're about to enter into a Q&A, and there will be also time for those questions then. Let's give it up for Sho one more time.